All right, so we're going to use some of the ideas that we just learned here, but we're going to look at some problems where we're going to have to partition the areas. We actually saw an example already with the sign example that we did at the very beginning of class today, where if we have sign and we want to find the total area enclosed by sign and the x-axis over its first period, we can break it up into two separate intervals and find the area of each of those and add them together. We're going to use that same idea here, but a slightly different looking example. So again, kind of like when we were finding the area enclosed by two curves, I'm going to give you some boundaries, and you're going to have to figure out what that shape looks like. So we're looking at the area of a region enclosed by three things. The first is the x-axis, or the line y equals 0. The second is the square root of x, and then the line x minus 2. And just like the last one, the best way to start here is to get an idea of what this looks like. These are all things that you should be able to draw pretty accurately without a calculator, I hope. I use the computer to do that, though. And so the region we're looking at is bounded by these two lines and also the x-axis right here. So we're going to get this region. Now, using the ideas that we've just talked about, we could find the area between the square root of x and x minus 2 fairly easily. But if I just take the integral of the square root of x minus x minus 2 from 0 to 4, I'm going to get not only that red area there, but I'm going to include some extra stuff here that I don't want. I don't want this stuff here. So what do? I want to start by saying I really like this example because there's about 57 different ways you can do this problem, and they're all going to give you the same answer, and they're all good methods. Some of them are better than others. And I'm going to be honest, we're going to start with one of the worst ways to do it. The trick here is we're going to break it up into two separate intervals. If we take the integral from 0 to 2 of just the square root of x, that's going to give us this area right here. And then what else?
Square root of x minus x minus 2 from 2 to 4.
Perfect. So then to find this area, we take the integral of the square root of x minus 2 from 2 to 4, and that's going to give us this area. So for one part, all we have to do is find the area between the square root of x and 0. So really just the square root of x and the x-axis, we can just do the integral of the square root of x. And then here we have to find the area between the square root of x and x minus 2. So we're going to break it up into two parts. All right? So to find the area of the first region, I'm going to color that one blue. To find the area of that, as Devin suggested, we can integrate from 0 to 2 the square root of x. And then to find the area of the red region, we can integrate from 2 to 4 of what?
Square root of x minus.
So we take the integral of the square root of x minus 2 with respect to x, and that's going to give us the area of this red region right here. Okay? Do you guys want to... Well, let's go ahead and evaluate it real quick. I think it'll be good practice. Take a minute to do that on your own. I want you to evaluate both of these. Try to do it without a calculator. Oh, man. And I'm going to point out a trick to you later, but you guys remember the sum and the difference rules for integrals? It basically says that we can split an integral up into different parts. So this integral right here, we could write as the integral from 2 to 4 of the square root of x minus the integral from 2 to 4 of x minus 2. Right? You guys agree with that? And then this blue area here, that's the integral from 0 to 2 of the square root of x with respect to x. And then what can we do with these two? We can combine those. We can write that, and this is a step that I would skip if I were doing this problem, but I can combine that into the integral from 0 to 4 of the square root of x. Now, I like this because when I evaluate this from 0 to 2, I'm going to be taking a square root of 2 and I'm going to have a radical in my answer. But when I evaluate this from 0 to 4, I can take the square root of both of these and I'm going to have nice clean numbers. So I like this integral better than these two because I'm not going to have any radicals in there. So that would be a little trick that you can use. If you don't do that, the square roots that you get from this integral and from this integral are going to fall out. So we end up getting 10/3 here. Cole pointed out, and I want to point this out to everybody, when Lewis suggested, I think this is what he suggested at least, finding the area under the square root from 0 to 4 and then subtracting this area right here, which was the same as this area right here. These integrals indicate exactly that. Finding the integral from 0 to 4 and then subtracting the integral from 2 to 4 of x minus 2, which would be this area right here. So those integrals that we ended up with show exactly that suggestion. We're going to look tomorrow at another way we can evaluate this, and we're going to be able to evaluate this with one single integral. It's just going to be moving along the y-axis instead of moving along the x-axis. So our Riemann sum rectangles, instead of being vertical, are going to be horizontal. And that's going to be really fun.